We're asked to find the minimum cost of a rectangular box of volume 190 cubic centimeters whose top and bottom cost 4 cents per square centimeter and whose sides cost 8 cents per square centimeter. To model the information, we will use the box shown here on the right, where the dimensions are x centimeters by y centimeters by z centimeters. To begin, we know the volume is equal to 190 cubic centimeters, and therefore V equals xyz equals 190. This is the constraint of the problem. And now let's set up the cost equation. We know the top and bottom cost 4 cents per square centimeter. Looking at the diagram, notice how the bottom is x centimeters by y centimeters, and so is the top. And therefore the total area of the top and bottom is 2 times x times y, and the cost is 4 cents per square centimeter, which means the total cost of the top and bottom would be 4 times 2xy. And now let's focus on the front and the back. The front has dimensions x centimeters by z centimeters, and so does the back. The total area of the front and back would be 2 times x times z at a cost of 8 cents per square centimeter, and therefore the cost of the front and back would be 8 times 2xz. And then finally for the right and left sides, the dimensions are y by z, and therefore the total area of the right and left sides would be 2 times y times z at a cost of 8 cents per square centimeter, giving us 8 times 2yz for the cost of the right and left sides. And now we want to minimize the cost function given the constraint of the volume. We will do this using the method of Lagrange multipliers, and therefore we need to write the cost function as f of x comma y comma z, and the constraint in the form of g of x comma y comma z equals 0. For the cost function, we have f of x comma y comma z equals 8xy plus 16xz plus 16yz. To form g, we set the volume equation equal to 0 by subtracting 190 on both sides, which gives us g of x comma y comma z equals xyz minus 190. And now to solve using Lagrange multipliers, we need to set up the system of equations shown here below using the partial derivatives as well as the constraint. Our first equation is the partial of f with respect to x equals lambda times the partial of g with respect to x. To find the partial of f with respect to x, we differentiate with respect to x, treating both y and z as constants. The partial of f with respect to x is 8y plus 16z plus 0, or just 8y plus 16z. And this is equal to lambda times the partial of g with respect to x. To find the partial of g with respect to x, we differentiate g with respect to x, treating y and z as constants, which gives us yz minus 0, or just yz. The second equation is the partial of f with respect to y equals lambda times the partial of g with respect to y. To find the partial of f with respect to y, we differentiate with respect to y, treating both x and z as constants, which gives us 8x plus 0 plus 16z, or 8x plus 16z, equals lambda times the partial of g with respect to y, which is just xz. Third equation is the partial of f with respect to z equals lambda times the partial of g with respect to z. For the partial of f with respect to z, we differentiate with respect to z, treating x and y as constants, which gives us 0 plus 16x plus 16y, or 16x plus 16y, and then we have equals lambda times the partial of g with respect to z, which is just xy. And our fourth equation is g of x comma y comma z equals 0, which in our case is xyz minus 190 equals 0. And now we need to solve the system of equations, which is where things get a little involved. Notice how I've numbered the equations to keep things organized. So we have our system of equations here at the top. For the first step, we're going to solve equation 1 for y and equation 2 for x. Once we do this, hopefully we'll see a relationship between x and y. So starting with equation 1, to solve for y, we need to have the terms with a factor of y on the same side. So we subtract lambda yz on both sides, and also subtract 16z on both sides. Then factor out y on the left, and then divide both sides by 8 minus lambda z, which gives us y equals negative 16z divided by the quantity 8 minus lambda z. And now we go to equation 2 and solve for x. We get the terms with the factor of x on the same side by subtracting lambda xz on both sides, and also subtracting 16z. Next, factor x from the left side, and then divide by the quantity 8 minus lambda z, which gives us x equals negative 16z divided by the quantity 8 minus lambda z. Now if we take a look at the expressions for x and y, notice how both x and y are equal to negative 16z divided by the quantity 8 minus lambda z. And therefore we can conclude that x is equal to y. For the next step, we're going to solve equation 2 for z and equation 3 for y, and hopefully see a relationship between z and y. So starting with equation 2, we now solve for z, which means we subtract lambda xz on both sides and also subtract 8x on both sides, which gives us a second equation. Next, we factor out z on the left and then divide by the quantity 16 minus lambda x, which gives us z equals negative 8x divided by the quantity 16 minus lambda x. Going to equation 3, we want to solve for y. First step, get the terms with the factor of y on the same side. So we subtract lambda xy on both sides and also subtract 16x on both sides. Next, factor out the common factor of y on the left and then divide by the quantity 16 minus lambda x on both sides, which gives us y equals a negative 16x divided by the quantity 16 minus lambda x. And now if we compare the expressions for both z and y, notice how the denominators are the same, but the numerators are not. The numerator for z is negative 8x, the numerator for y is negative 16x. But also notice how negative 8x times 2 does give us negative 16x, which means if we multiply z by 2, it would be equal to y. Or we can say y is equal to 2z. And we also know x is equal to y, so we could also say x is equal to 2z. Now that we have relationships among x, y, and z, we can solve for x, y, and z using equation 4, the constraint. Let's do this on the next slide. Again, we just found that x is equal to y, and also y is equal to 2z, which is also equal to x. If we wanted to solve for z, notice how we would divide by 2. We can also say z is equal to 1/2 y, as well as 1/2 x. So now we'll go to equation 4. Let's go ahead and write equation 4 as x, y, z equals 190. And now let's substitute x for y and 1/2 x for z. So we have an equation in one variable. We would have x times z is 1/2 x equals 190. Multiplying on the left, we have 1/2 x cubed equals 190. To solve for x cubed, we multiply both sides by 2, which gives us x cubed equals 380. And now to solve for x, we take the cube root of both sides of the equation. And now we know that x is equal to the cube root of 380. We also know x equals y, so we also know y is equal to the cube root of 380. And we also know z is equal to 1/2 x or 1/2 y, and therefore z is equal to 1/2 times the cube root of 380. Well, if we want the cube root of 380 divided by 2. And of course, all of these units would be centimeters. So we just found the dimensions of the box where the volume is 190 cubic centimeters and the cost is minimized. But the question here is to find the minimum cost. So now we take these values of x, y, and z and substitute them back into our cost function or cost equation given here. I've already done this to save some time. I've substituted the cube root of 380 for both x and y, and the cube root of 380 divided by 2 for z. Looking at the second and third products, notice 16 divided by 2 is 8 here as well as here, which means we can write this product as 24 times the square of the cube root of 380. And now we go to the calculator. And remember, because we set up the cost equation in cents, this cost will be in cents, which gives us approximately 1,259 cents. Let's go ahead and convert this to dollars and cents by dividing by 100, because there's 100 cents in a dollar. The minimum cost is approximately $12.59. I hope you found this helpful.